It's a great idea, Jackson. All right, good morning, ladies and gentlemen. Welcome to this very, very nice Wednesday. All right, first off, I need you to get your notes out as well as a calculator. All right, so we ended yesterday's discussion with the electromagnetic spectrum and the, as I said, nearly Grammy Award-winning song, which hopefully you all went back and listened to a couple times just to really catch the essence of that song. I'll post a video of it so you can watch it now. It's great. I love it. Anyway, you will hear the song again because it does help you. Okay, and we related the various types of electromagnetic radiation to frequency and wavelength. Now, I mentioned in yesterday's class the type of relationship that frequency and wavelength have. Does anybody remember what that is? Inverse, yes. When one goes up, the other goes down. And so if you want to have radiation with a really high energy, you're going to have radiation with really high frequency and a really small wavelength. Okay? So today what we're going to continue our discussion on is we're still kind of in the time of atomic expansion in terms of our knowledge. And so we start getting introducing individuals like Einstein to the game of trying to figure out how atoms work. Okay, and so we talked yesterday about the wave nature of light. Now we're going to talk about the particle nature of light. Light is weird. Light can be two things at the same time. And thankfully, it is weird. Because otherwise, life would just not be the same. Okay? I mentioned yesterday about the concept of quantum mechanics. Okay? And we just really introduce it to you here. Okay? What the quantum concept is that the wave model of light cannot simply explain all of light's characteristics. Cannot explain why heated objects emit only certain frequencies of light at a given temperature. Some of the examples here, the bottom right, you've got the rings on the stove. As you turn on the stove, it passes electricity through it. Depending on how much electricity you pass through it, it's going to essentially change the color that those rings glow. A light bulb. You know, we have various wattages of light bulb. And each one of those wattages can be bright, dim. We even have soft white, cool white, warm white. We can manipulate light once we started understanding the intricacies, the characteristics of it. Okay? Another example is why some metals emit electrons when colored light of a specific frequency shines on them. That's a really cool one. And we're going to talk about that. That's what's called the photoelectric effect. In kind of our stepping towards our understanding, continuing with the guy by the name of Max Planck. Now, has anybody seen the third season of Stranger Things? Just a couple of you. If you haven't even watched the series, do so. It's fantastic. Well, Thought there was going to be a larger contingent of you who had seen it. Anyway, Max Planck, more so his number that he developed, played a vital role in season 3 of Stranger Things. Okay, he was a German physicist who in 1900 began searching for a model to explain light's characteristics. And what he found was that matter can gain or lose energy in only small, specific amounts that he called quanta. And a quanta is a small, specific amount of energy. So, they took Planck's results of his experiments and, as we expected, ran with it. He went ahead and said that the emitted light energy from quote-unquote glowing objects must be quantized. He demonstrated mathematically that the energy of a quantum is related to the frequency of the emitted radiation. So now we have a link between the frequency or the energy of radiation to that of the amount of energy present. And he gave us this equation. It's another simple equation, much like what we saw yesterday with the speed of light, frequency, and wavelength. Here, we have E, which is the energy of a quantum, is equal to H times nu. Again, what is nu and U? What does that represent? Not the wavelength. Frequency. Very good. And what H is, it is Planck's constant. If you can't read the value, here it is. 6.626. That boba again.
It was a top, don't worry.
What?
Yeah.
So 6.626 times 10 to the negative 34th. Think how small that is. 10 to the, oops, here. 10 to the negative 34th. And Planck's constant has a unit of joule times seconds. Now, if you want to jot this down on your notes as well, when you solve for this equation, E equals H times nu, when you are solving for E, which again is energy, your label is joules, or capital J. Because the S in Planck's constant will cancel out the label for frequency, which again was S to the minus 1, which leaves us with joules. Oops, sorry. And as we just said, nu, or fancy V, represents the frequency of radiation. Now, before we apply Planck's constant and Planck's formula for quantum, let's talk about that photoelectric effect, okay? What the photoelectric effect is when electrons, as we call photoelectrons, are emitted from a metal surface when light of a certain frequency shines on it. This was a phenomenon that was really, really, really baffling scientists. They would use various energies, various colors of light, and had a system set up to where they could determine if the metal surface they were shining that light on was actually having its electrons knocked off. Once they started figuring that out, they were able to figure out the amount of energy associated with each light. Again, that wave model predicts that given enough time, even low energy, low frequency light would accumulate and supply enough energy to eject photoelectrons from a metal. But metal will not eject photoelectrons that below a specific frequency of incident light, meaning just light directed towards it. But incident light is just light directed towards it. So if we look at silver, and they did numerous studies of various types of metal. In this example, they shot light, various wavelengths of light at a silver surface. And they found that any light that had a frequency less than 1.14 times 10 to the 15th hertz would not and could not eject the photoelectrons off the silver surface. So they found that there are thresholds for various metals. But once they would shine a light that is equal to or greater than this frequency of light, of this 1.14 times 10 to the 15th hertz, would cause a photoelectron to be ejected off of the silver surface. All right. And really, this is the same concept as to what solar panels use. They use materials who are going to interact with the light given off by the sun. And that energy of the light given off by the sun is capable of knocking electrons off of the material in the solar panel, which those electrons are then collected through the system and used as energy to whatever it is connected to. Like yesterday when I tried to use a calculator, okay? There was not enough energy with the minimal amount of light in here to strike this solar surface and cause the ejection, therefore flow of electrons to power the battery. It wasn't until I turned on these lights that I had enough energy. Here comes your boy, Albert Einstein. In 1905, little Albert proposed that light has a dual nature. He said a beam of light has many wave-like characteristics and thought of them as a stream of tiny particles or bundles of energy called photons. So you have Planck calling them quantum, and you have Einstein calling them photons. Particles or bundles of energy. So Einstein went on to define a photon as a particle of electromagnetic radiation with no mass that carries a quantum of energy. He went on to propose that the energy of a photon of light must have a certain minimum or threshold value to cause the ejection of a photoelectron. These photons must possess a minimum amount of energy to free that electron from an atom of the metal. A photon's energy requires a minimum amount of energy, and then we're gonna be utilizing Planck's equation to help us determine the minimum amount of energy. Again, the energy of a photon is in joules. We know Planck's constant. We wrote it down a few slides ago, but I'll say it again. It's 6.626 times 10 to the negative 34th joule times second. Again, nu is frequency. So we're going to calculate a couple of problems here. First one, you want to have your calculators readily available. First one says, what is the energy of a photon from the violet portion of the rainbow if it has a frequency of 7.23 times 10 to the 14th s to the minus 1? So let's take a peek. All right, so first, our formula. E is equal to Planck's constant, h, times v. So we're solving for E, so we don't have to do any rearranging here. All we have to do is plug in our values. Now, our first value is Planck's constant, okay? So again, I'm using parentheses, 6.626 times 10 to the negative 34th joules times second, close parentheses. Excuse me. And we multiply by the given frequency in the problem of the violet light, which they said had a frequency of 7.23 times 10 to the 14th s to the minus 1. I'm going to zoom out so you can see this a little better. So again, just like yesterday, you need to use parentheses around each value because that tells your calculator that you are following a specific set of instructions when calculating this. So go ahead. I want to make sure that you are typing this in your calculator correctly. Go ahead and solve for this. Let everybody have a few moments to do so. Who has an answer I'd like to share? Anybody? Very good. And what unit would you put, or what label would you put for your answer? Very good. 4.79 times 10 to the negative 19th joules. Double check your calculation. That's what you should be getting. Okay. We got one more here. 3B. What is the energy of a photon that has a frequency of 9.50 times 10 to the 13th hertz? So again, they're using, in these two problems, they've used both of the labels that you can use for frequency, s to the minus 1 and hertz. And like I said yesterday, when you are solving it mathematically, using s to the minus 1 is better because that's a unit that you can cancel out when needed, okay? So we are going to follow a very similar pattern here. Again, we're solving for E. And so I take my H, Planck's constant, 6.626 times 10 to the negative 34th joules times second, and multiply it by the frequency given to us in the problem, which was 9.50 times 10 to the 15th hertz. But for now, for here, I'm going to put s to the minus 1 because I need to cancel that out with this s. So again, I want you to calculate it out. I like the first three numbers. What? You got positive 20? Hornbacker, what'd you get?
It's to the 13th.
Did I make a boo-boo? Wouldn't be. You're right. I stand corrected. Thank you, thank you, thank you. Actually, I had 13 written on my paper. I just can't read my handwriting. All right, let's try that again. So I need to change my answer. So what'd you get? 20? Negative 20. It's always good to have people check your work. Okay. And again, it's in joules. Very good. You fix that. All right. Questions on how you use this. Again, I'll say it every time we come into a formula. Anytime we have a formula, we can always rearrange this formula to solve for any three of the variables. Well, with the exception of Planck's constant, because that's a constant. But we could use it to solve frequency if we already knew the energy. Okay? So always keep that in mind. So we are almost done for the day. For the atomic emission spectra of an element is defined as a set of frequencies of the electromagnetic waves emitted by the atoms of an element. How this occurs is the atoms absorb energy, and once they do that, they become excited. The atoms become excited, which when you absorb energy and become excited, you therefore become unstable in terms of an atom. And so an atom wants to get rid of that energy. It's like if you had 3 bangs before you went to school, okay, which you don't do. Eventually you get all jittery and worked up, and that's not how you're supposed to be, okay? Your body knows that. And so in order to get rid of that, you just kind of lash out, right? Well, how atoms get rid of that energy so that it becomes more stable again is they emit energy in the form of light. So anytime you see light, it's really the result of an atom becoming excited and then releasing the energy so it can become more stable. Now, only photons having certain specific energies are going to be emitted. And we can determine those using the formula we just used in the previous slide. And just like the characteristics and makeup of each element's atomic emission spectra will also be unique. And in fact, over on the wall beneath the sloth over there is a periodic table of emission spectra. So you'll see that there is not one element that is like another. So we can use this emission spectra, since they are unique to each element, as a means to determine what an unknown substance is, or substances if it's in a compound. Because only certain colors will appear in the element's atomic emission spectra, and only specific frequencies of light will be emitted from a specific element's atoms. So if we look at neon signs, okay? Light in a neon sign is produced when electricity is passed through a tube that is going to be filled with a neon gas. When that happens, you excite the neon gases. Now again, we get various colors of these lights through using various elements in their gas state. Not just neon, we just associate neon with these signs. And so those neon atoms become excited. They don't like it so much. They're too high in energy, so they release that energy in the form of light. And typically when you see a neon light that is yellow, that is the signature color that is typically emitted from neon. But if we were to take that yellow light and use a form of a prism or machinery that could break that light apart, you would see the individual frequencies of light that make up that neon's color. Now, when strontium nitrate is placed in a flame, as we see down here, that flame carries energy, carries heat energy, but it's energy all the same. That heat energy transfers its energy to the atoms in the strontium, and the strontium atoms get excited, then they release that energy they received in the form of a red colored flame, which they have been able to, when they did this, they figured out that if they could really ignite various substances, we could get a result of a various color, which is kind of how the idea of fireworks occur. That's why you get those various colors when you see those big, huge, booming fireworks. They are made up of various elements that burn and emit different colors because they are absorbing energy from the explosion. So that's really how fireworks work. All right, tomorrow, do not forget a calculator. Tomorrow is a homework check. Once the homework check is done,